In this frames and machines problem, we are trying to find the external reactions at A, B, and D to maintain static equilibrium in our system. So we want to find all the reactions at those 3 points, at A, B, and D. So if we look at the setup of this, of how all of our members are put together, we have this blue member ABC, and then this green member CD, and they are connected together with this peg and slot. If we look at the external supports we have a pin at A, we have a rocker at B, and we have a pin at D. So externally, this is going to be statically indeterminate. We're going to have 5 support reactions, 2 at A, 1 at B, 2 at D. So it's statically indeterminate, and if we look at the 2 members, the blue one and the green one, the blue one has a peg and slot connection, a pin connection, and a rocker, so we cannot conclude it's a 2-force member. And CD has a peg and slot at C, it has a pin at D, and it has an external forcing 600 newtons along its midspan. So that too we cannot conclude as a 2-force member. So this is not a truss structure. We have to treat it as a frames and machines problem. So as far as the free body diagrams go, because it's statically indeterminate, as most frames and machines problems are going to be, I want to draw the free body diagrams of the individual members. So member CD will get its own picture, and ABC will get its own picture too. And they will all share the same coordinate system. All right, so I'm not drawing the external picture, so I am not going to keep ABC and CD together in a picture. I could draw that picture, but I already know it's going to have 5 support reactions, so I'm going to break it up into its pieces, CD and ABC. Which one I start with really doesn't matter, but looking at ABC, I know that unknowns it's going to introduce right away are going to be 5, 2 or 4, 2 at A, 1 at B, 1 at C. In CD, though, I'm going to have 1 at C and 2 at D. So with experience and practice, you'll be able to just by inspection see this up front. Whether I drew ABC first or CD, it wouldn't matter, but I'm going to choose to draw CD first and then get its equations first. And we'll see that algebraically it will be easier, but as long as we have a solvable system, it really doesn't matter the order that we do this in. All right, so I'm going to copy exactly the external forces and couples acting on this. There's only the force of 600 newtons acting at the midway between D and C. So that's going to be 1.5 meters, 1.5 meters. Okay. And CD does not know that that 800 Newton meter couple is happening. That is acting on ABC. Through the connection point at C, it will be affected by it, but that's not going to be in this picture. And this is making a 45-degree angle with the negative x-axis. I copied exactly that external applied load, the 600 newtons. Now I have to look at what's happening at my internal and external supports. At D, I have a pin connection, an external connection there. So I can model that as a horizontal and a vertical component, a dx and a dy. And at C, I'll mark this, that's a right angle. At C, I have that peg and slot connection. So this is just a little bit trickier to think about, but just like with other supports, internal or external, we want to think, because of that peg and slot connection, how can CD translate and rotate at point C, and what is prevented? So let's think about translations first. Because the slot is aligned with the CD axis, the member CD can translate along the CD axis. It's not going to prevent that motion at all. However, because of that pin connection, it cannot translate orthogonal to that axis. So the normal direction to CD is going to be prevented translation-wise. However, parallel to CD, it is able to move. So only one axis is restricted, so I know that along this axis I just drew, that there is going to be a force. Now I don't know what direction that force should be in necessarily up front, so I know its direction is along this axis. I don't know its magnitude, and I don't know if it should point up and right or down and left. But it really doesn't matter too much as long as I'm consistent. So I am going to draw in this picture up and to the right. And I know that that is orthogonal to this CD axis. And I will call this C. So this is point C and this is force C. So I am using C twice here. So I'll make this so I know it's a point. All right, we have that internal reaction force of C, I'm assuming is up and right in this picture. The applied force of 600 down and left, copied exactly from the picture. And D is a pin reaction. I'll assume dx right, dy up as the positive directions. All right, so in free body diagram 1, if we see by starting here, we have a total of 3 unknowns, and we have a 2D rigid body. So I'm actually going to start writing equations, and then I'll come back. So from free body diagram 1, if we look, we have a pin at D. So I'm actually going to start this one with a moment around point D. And remember, a rule of thumb is when we have do the moment equation, we are going to usually use a point that is only in one picture, which in this case, D is only in one picture and D is a pin. So for both of those reasons, D is a good choice to take the moment about. But as always, if we take the moment about any point, the equation we write is still going to be true. So what causes a moment around point D? Dx and dy do not. We purposely chose D to eliminate them. We are going to have a 600 Newton force, and its perpendicular distance from D is 1.5. So this is one of those more somewhat rare cases where we just are going to multiply the force times the distance because we actually know that perpendicular distance is along the CD axis. Because 600 newtons is orthogonal to the CD axis, therefore we know 1.5 meters. We don't, in this case, have to break the 600 into a vertical and a horizontal and then individually get the horizontal and vertical distances because it's orthogonal to the axis CD. So that makes this a little bit easier, and that is going to, around D, be a positive moment. I'll just put a plus sign there so we remember that we did already account for the direction. And there's a moment caused by C, and that is going to have a perpendicular distance of 3 meters away. So 3 times C, and that is going to be clockwise, so negative. Once again, since C is orthogonal to the CD axis, force C is orthogonal to the CD axis, I do know its perpendicular distance is 3 here, so I can just write it down that way. And by starting it with equation 1, when we get to the solve step, I'll write other equations first, but we can solve for force C just from equation 1 right now. But I'll write the 3 equations and then solve them, then go back and see that we will need more free body diagrams. Now, let's write the forces. Let's do X in picture 1. We are going to have dx minus, this 600 is making a 45-degree angle with the vertical, also with the horizontal. So we need its horizontal component. I'll just write it as 1 over root 2 or root 2 over 2, the same thing. It's fine mixing a radical in the denominator since we're going to get the decimal equivalent anyway in the end. So 1 over root 2, that is the sine or the cosine of 45 degrees, but I'll just write it this way. So that's going to be pointing to the left, plus C is also making a 45-degree angle. Since it is going to be orthogonal to this, I don't really need this since it's already indicated, but I'll put in its directions just to remind us. And that's going to be pointing to the right, so that is positive 1 over root 2 times C. And by the time we get to equation 2, we'll already know the value of C, so we'll be able to find dx. And then the y direction, dy is positive. We have 600 cosine or sine 45 degrees, which is 1 over root 2. That is going to be down, and plus 1 over root 2 times c, since that is pointing up. So looking at the three equations I have so far, I have three equations, three unknowns. So I'm actually going to solve them as we go. So in equation 1, I can find that c is 300 newtons. My assumption of in this picture up and right was correct. It's an internal force, so I'm not going to indicate its direction because, as we'll see when we draw the second free body diagram, it's open to a little bit of interpretation. Now that we know c, we can put that into equation 2 and find that dx is a positive 212 newtons. The positive means, because it's an external reaction, that my assumption was correct. It's to the right. And then putting c into equation 3, we get that dy is actually also positive 212 newtons. So my assumption of up was correct because I get a positive value. So I've found the reactions at D. I have found the internal support force C, which I'm going to need in the next step. But so far D has been found. So I'll mark that off, that part at least is done. I still need A and B. And we'll notice then free body diagram 1, A and B did not appear. So clearly we're going to need more free body diagrams, more equations. For my second free body diagram, now I can draw ABC. I have A, B, and then point C here, 2 meters, 2 meters. I'll start with the external loads, forces and couples, of which I have one. I have this applied couple of 800 Newton meters at point A. And that's the only applied load I have here, so I can put in my external supports next. I have a pin at A, so I can draw its components, AX and AY. Again, I'll assume positive right, positive up, and let the math tell me if that's right or wrong. At point B, I have a rocker. The rocker allows translation, in this case horizontally, at least a little bit. It does not prevent rotation, but it does prevent translation downward. So B, I will call it, must be pointing up. And those are the two external supports, A and B. So now I have to deal with C. One thing I should point out from picture 1, I knew it had one force because it allowed translation along the CD axis but not orthogonal to it. I forgot to specifically point out that rotation at point C is allowed. That peg and slot does not prevent, just from the viewpoint of C, does not prevent CD from rotating around point C. So no couple at C. So now in this picture 2, I also have C in this picture. Now, in picture 1, I assumed it was up and to the right. This is an internal support. Everything in the second picture, because it's two members that are connected, and no more than two, but when two members are connected, whatever I assumed in the first picture, I must assume the equal and opposite in the other matching half of the picture. So up and right in picture 1, automatically down and left in this picture. It's already decided for me. Right? Because really what I'm modeling is picture 1, that force C is actually what is ABC doing to member CD. I'm assuming it's pushing it up and to the right. Because forces act equal and opposite, in picture 2, I'm obligated to have the opposite, because really what that C force is what is member CD doing to ABC. So whatever ABC does to CD will be the opposite of what CD does to ABC. So this internal force C must be drawn down and to the left. Now I do already know it's the number, the numerical value for it, but I'm not going to use that information right now. I am just drawing this picture, and then algebraically I am going to write the equilibrium equation. Then I can put in the actual value I have for C. But this must be what my picture looks like because it's an equal and opposite force in picture 2 as it was in picture 1. So equal and opposite, there was no couple at C, so I don't draw a couple here. And there was only one force in a known direction, which I copied here as well. So at this point, I can make a little bit of room. I write equation 4. So in this case, I'm going to start with the moment around point A in picture 2. Because AX and AY both appear in that, rule of thumb, use a point that only is in one picture. Well, don't use C because it appears in 2 pictures, but I'll choose A. It eliminates AX and AY. So I'm going to have in this equation then a negative 800 because I have that couple that's acting clockwise, which is a negative direction, plus the moment caused by B, which is 2 meters away. My base units are newtons and meters here. And then minus, I have the vertical component of C, which is 1 over root 2 times C, and its distance is 4 from A. And that vertical component of C, just to illustrate it, the vertical component is going to cause a clockwise or negative moment, and the horizontal component has its line of action pass through A, so it will not appear. At this point in my solve, I'll get to it when I get back into the solve step. I already know C, so I'll be able to find B easily. Now I can proceed with force equations. Let's do x direction is going to be my AX minus 1 over root 2 times C. And again, I already know C, so I can find AX easily from that. And then the y direction, I will have AY, I'm assuming is up, B, which I will already know by this point, minus the vertical component of C, which is 1 over root 2. And again, by this point I will know C and I will know B, so AY will be easy to find. Coming into the solve, C I already know, so I can put that into my equation 4 and I can figure out B. B is my external force, 824 newtons. It's positive, so it is up. 5 also depends on C. I can figure out then AX is going to be 212 newtons. It's positive. It's external, so I do want to indicate its direction. Positive means my assumption was correct. It does point to the right. And I'll make that a little bit cleaner here. And finally, 6, I need C and B. So just so it's clear where I am getting this, AY is then easy to find, is a negative 612 newtons. I assumed it was up, it's negative, it's actually then pointing down. Again, back to the pictures here. The externals, the direction will matter in that there's a physical interpretation for a positive or a negative with these external reactions. However, with C, notice here I found it was positive 300. I don't want to draw a direction on there because in one picture, picture 1, it was indeed up and to the right, and in picture 2, it was indeed down and to the left. But with the internal reactions, because they act in equal and opposite ways in the multiple pictures, the interpretation of direction doesn't really make sense universally because it behaves one way in one picture and the opposite in the other. And finally, I'll point out, I arbitrarily decided to draw in picture 1 C up and to the right. I could have decided to draw it down and to the left. And what would that have done? Well, in every equation, the C term would have been negative in equations 1, 2, and 3. And then that would mean I would have found that C was negative 300 newtons. That's okay, it just meant my assumption was wrong. Had I drawn it in picture 1 down and to the left, then in picture 2, it would have had to have been up and to the right, which means that equations 4, 5, and 6, my C terms would have also all been negated. In fact, they would have been actually positive then in 4, 5, and 6. However, I would have found in equation 1 that C was negative 300, so everything would have worked out the same way. It's just that my assumption was the opposite of the direction of C. So if C, we got 300 drawing it up and to the right, or negative 300 drawing it down and to the left in picture 1, all of my other answers would have been consistent. But again, I would have been obligated to draw it equal and opposite in picture 2, however I drew it in picture 1.